Before we get started, please make sure that you have printed out the PowerPoint slides so that you can make notes as we continue through this PowerPoint presentation. We're going to take a little bit of time to talk about working with square roots of negatives, and we're going to look at the quadratic equation x squared plus 1. If we were to try to solve this by setting it equal to 0, we would have x squared equals -1. And as you may recall from previous math classes, when you try to take the square root of a negative number, this causes all kinds of problems. So mathematicians invented imaginary numbers to help us deal with the square roots of negatives, which is what's written on your paper much better than what's written on the slide here. We would have x equals plus or minus the square root of -1, and the square root of -1 was developed to give us plus or minus the imaginary number I. Every time we have a negative or the square root of a negative, we can use our imaginary numbers to help us take the square root. One of the properties that we used was if we took the square root of -1 times the square root of -1, that would be like taking I times I, or I squared. That would be giving us -1, which is where we get I squared equals -1. We can then use if we have the square root of a negative, let's say we have the square root of -5, we could take out the negative in it as the imaginary number and leave behind the square root of 5, because we can't take the square root of 5 any further. If we happen to have something like the square root of -4, the square root of the negative would give us I, and the square root of 4 gives us 2, so that would be 2I. We're going to spend a couple minutes practicing with imaginary numbers in the next few examples. So a complex number has both our imaginary units as well as a real number. So we might see something like 3 minus 2I, and that's a complex number. And we're going to use our complex numbers as we work through some of the properties in the next few slides. Now, in terms of adding and subtracting complex numbers, we add the like components together. So in our first example here, it would simply be 1 minus 3, which sounds like -2, and -2 minus 4i, -2i minus 4i would give us -6i. And I'm making sure that my final answer here has the real number first and the imaginary number second. When we multiply, as we have in our second example, this would be just like FOILing. So I would multiply 1 times 3 and 1 times 4i and -2i times 3 and then -2i times 4i. Then I would check to see if I have any like terms, and I certainly do. But wait, I squared seems to be something that we had from before. I squared was the same thing as -1. So this -8i squared is really 8. So I essentially have 3 plus 8 minus 2i, which sounds like 11 minus 2i. And that is my final answer, not the trinomial that involved I squared. For this third problem here, where I have to divide with 3 minus 4i, I essentially have a square root in the denominator. So to get rid of something with a square root in the denominator, way back when, you might have learned about multiplying by a conjugate. So what is the conjugate of 3 minus 4i? It's 3 plus 4i. So whatever the sign is here, I need to use the opposite here. I don't have to worry about what the 3 says. It's not important. It's whatever the one with the square root, that sign. I need one positive and one negative. And anything I multiply in the denominator, I have to multiply by in the numerator. Now, the work that we just did in problem 2 is in fact our numerator here. So I can write 11 minus 2i. And now I need to do the work with multiplying my denominator out. So 3 times 3 gives me 9. 3 times 4i is 12i. Negative 4i times 3. I'm going to put some work over there. And negative 4i times positive 4i is minus 16i squared. And then I'm going to work down. So I have 11 minus 2i. And as I take a look at what happened in my denominator here, my positive 12i and my negative 12i canceled out. That's why we have one negative and one positive. So I really have 9 minus 16i squared, which after all is a negative 1. So that's 9 plus 16, or 25. So I have managed to go from a problem that had a negative square root in the bottom, that's what the I is telling us, to a problem that has a number of 25, no square roots anywhere. I have a square root in the numerator, but that's allowed. And we're done. So complex numbers come in pairs. If we have a plus bi, the conjugate of it is the a minus bi. And a notation for this happens to be the bar. For instance, if we have 3 plus 2i, the bar over top of it is telling us about the conjugate, 3 minus 2i. That's what we have down here. It's telling us about the conjugate. Maybe. On the other hand, if we don't have imaginary numbers, the bar of like 6 bar is just giving us the number 6. If we have square roots involved, like the 3 plus the square root of 5, you may have done this a while back. We would have the 3 minus the square root of 5. We don't really need to spend a lot of time on the properties of the conjugates, but we need to know what the conjugate is if we have to get rid of the square root in the denominator. Now on your paper, it looks the polynomial here is written much nicer. It would be f of x equals x squared minus 2x plus 5. And we're trying to figure out what the zeros of this polynomial would be. So we want to take our quadratic and set it equal to 0. So we have x squared minus 2x plus 5. So the fastest way of doing this would be factoring. So I'm looking for factors of 5 that add to negative 2. And I can think of 5 and 1, and none of those add to 2, which means it's not factorable. My other option is the quadratic formula. And that's where we're headed. So x equals 2 plus or minus square root of negative 2 squared minus 4 times 1 times 5 all over 2 times 1, which is going to give us 2 plus or minus the square root of 4 minus 20 is negative 16 all over 2. Square root of negative 16 excuse me, would be 4i, and that would be part of the reason why we had trouble factoring it. It's because our roots are imaginary. And so it turns out if I divide 2 into both of the values in the numerator, I have x equals 1 plus or minus 2i. Those are the imaginary zeros that I have for my quadratic. If I wanted to write this out as linear factors, I would say that I have x minus each of my factors. And that's where these brackets are coming from. 1 plus 2i, and then I would have x minus 1 minus 2i. So I have completely factored my original quadratic. This is in factored form. These are the zeros. Depending on what the question was asking for, it was actually asking us for the zeros. Now, the fundamental theorem of algebra is not that helpful for what we've been looking at. What the fundamental theorem of algebra does is it guarantees us complex zeros if we have complex coefficients. We don't see complex coefficients all that often because that means our coefficients have to have imaginary numbers in them. And this is an example of something called an existence theorem. It does not tell us how to find our zeros. And we need to use much higher level mathematics to prove this theorem. It took hundreds of years for the proof to be completely developed, so that's why we say it's neither fundamental nor algebraic, but it will help us find some of those complex zeros like we found in the last one where we used the quadratic formula to get our last couple zeros. With the complex factorization theorem, we know that if we have a complex zero, if we have one of them, we also have the second one of the pair. So if we have a complex zero with the minus sign, we would have the other one that has the plus sign in between the real and the imaginary portion. This also works with multiplicities, and that information would have to be given to you as part of the problem, and we'll see some examples like this as we work through the next couple slides. Okay, so if I take a look at this 5th degree polynomial, and I need to factor this. As a 5th degree polynomial, I need to get this down to a quadratic before I can get to the quadratic formula. So I'm looking at all of the possible p over q's that I could have with this, which means I'm looking at the 1 and the 12. And unfortunately, 12 has a bunch of factors. So it's basically going to be plus or minus 1 over all the factors of 12. So 12, 6, 2, 3, and 4, which is an awful lot of fractions, and so I go to my graphing calculator, and I'm going to check and see if any of those appear reasonable to test using synthetic division. And what I see from my graphing calculator is that 1/2 like I zoomed in, and it looked like 1/2 was a pretty good approximation. And the way that the 1/2 occurred, it looked like the 1/2 touched and then went back up. So I bet 1/2 is going to have to work twice. I would have a multiplicity of 2 on that. So I'm going to try 1/2 twice. The other one is a little harder to see. I can't tell if it's, I don't think it's 1/2, but I can't tell if it's 1/3 or 1/4. So if you want to investigate that a little further on your graphing calculator to see if 1/3 or 1/4 on the negative side works better, or we're going to be doing synthetic division just to see which one works. So let's go see what we can do with 1/2 in our synthetic division. And lo and behold, when I used the 1/2, 1/2 gave me a remainder of 0, which indicates that 1/2 is in fact a 0 of the original 5th degree polynomial. And I'm going to try it again because it really did look like it had a multiplicity of 2. So let's see how that works out. And so I can tell that I'm in trouble here because I'm getting a remainder of 1. And as I look back at my work, I can see right here that I should have had a -2, and then I would get a remainder of 0 the way I was anticipating. So it helps if you carry correctly. And then in fact I do have a remainder of 0, which tells me that 1/2 does in fact go into the polynomial twice. It has a multiplicity of 2, but I now have a cubic function here, and I really need to know if on my graph it crossed at -1/3 or at -1/4, so I'm going to use my graphing calculator and investigate, and it looks like -1/3 is a good choice. So I'm going to use -1/3, and this is why we like technology to help narrow things down for us. I can't just use my graphing calculator because 2 of my zeros are missing. I only have 3 that are showing up. 2 of them are not evident from my graph, so I can't just make them up. So let me finish this here. And lo and behold, -1/3 was a good choice because I got another remainder of 0. So what I have from my suppressed polynomial is 12x squared minus 12x plus 12 equals 0. First thing I'm going to do is factor out a 12. I have x squared minus x plus 1. And if I use the quadratic formula, wind up with x equals positive 1 plus or minus the square root of negative 3 all over 2. And with having a square root of negative 3, that's telling me that I've got imaginary roots or complex roots. And that's part of the reason why they were not crossing the x-axis anywhere. So if I want to take all of my factors and write them out, this is going to be very interesting here. Alright, so with my 1/2, that would give me a factor of 2x minus 1. And if I know that I have 1/2 twice, I would have to square that. If I have the negative 1/3, that would give me a 3x plus 1, and I only have one of those, so it's to the first degree. And then with my complex ones, it's divided by 2, so that would give me a 2x, and then I'm going to have minus all the stuff in the numerator, 1 plus I square root of 3, and 2x minus 1 minus I square root of 3. So that is factoring the original polynomial. And if you really want to have a good time, you can you can multiply all of that out and hope you don't make any silly mistakes along the way to make sure you get a 5th degree polynomial with a first term, a leading coefficient with 12x to the 5th, and a constant term of 1. I'll leave that to you. Okay, so the two theorems that we have here, the first one is talking about the complex conjugates, so that if you have one conjugate, or if you have one 0 that has a plus bi, you are guaranteed having a minus bi as the other 0. The factorization theorem is saying that we can factor our polynomial all the way down into all the sets of parentheses, like this, either into linear or into quadratic factors, like we were doing in the previous example. Now, in this one, it's a real pain, but we're taking x to the 4th plus 64, and we're using synthetic division with x plus 2i. If we have x plus 2i as a 0, we would also have, 2 plus 2i, we would also have 2 minus 2i as a 0, and then we could, those would be our factors over the complex numbers. We would go from a 4th degree, this would give us to x to the 3rd, and then this would get us to x squared. Once we have a quadratic, we could factor using factoring or the quadratic formula to figure out getting the reals. If you were so inclined, you could spend some time using synthetic division with 2 plus 2i out in front, 2 plus 2i in your synthetic division, and then you'd have 1 for x to the 4th, 0 for x to the 3rd, 0 for x squared, and 64, and I'm leaving tons of room because you're going to have 2 plus 2i taking up a lot of space. You can have fun taking that any further. Now we should be able to take our information from multiplicities, from our zeros that are imaginary, and from our information about the general shape of the graph to be able to put together some sort of polynomial that's all written out. So let's see. If the graph touches but doesn't cross, that tells me that we have a multiplicity of 2. So it's saying that this is x equals 1/3. So I'm going to back that up. So we have a 0 at 3x, let's see, minus 1. And if we've got a multiplicity of 2, that would tell me the factor 3x minus 1 squared comes from this piece of information. From this piece, 3i is a 0. Well, if we have 3i, we also have negative 3i. And then if we have, as it's going to infinity, our graph is going down. And if it goes to infinity, our graph is going, to negative infinity, our graph is going down. So the end behavior on our graph is doing this. So I have 2, 3, 4. I need a 4th degree. So this is telling me I have a negative 4th degree from my end behavior and from the multiplicity 2 and my positive and negative imaginaries. And so if x equals 3i, that tells me I have the factor x plus 3i and x minus 3i. Oops. So this is with the plus 3i, and then this is the minus 3i. So if I put all of these together, I would have a polynomial. Let's see, p of x, 3x minus 1 squared, and then x minus 3i, and x plus 3i. And if I look at my degree, that's x squared, that's x, that's x. That's a 4th degree, but this is looking like a positive 4th degree, so I need a big old negative sign out in front to make sure that this graph is going to negative infinity.